Welcome to the second part of the lectures on modelling karst hydrology. I don't have any exciting intro pictures to show you about modelling karst hydrology, so instead you get a picture of my spaniel, Budley, who's sleeping through the whole of this pre-recorded lecture series. We just moved, you're honoured. Anyway, on this slide is a picture of a model of something. Can you tell me what it is? I'll be asking in class. To recap, we're going to use caves as observatories of groundwater recharge, and we can use some of that data to also build some models to understand how the hydrology of those systems work. So that's karst hydrology, and this slide talks about karst hydrology and how that relates to caves. Some of this is a recap from previous material. The most common caves are those formed in limestone, which is calcium carbonate, which you should know is CaCO3. We covered that in the water chemistry topic. And you should also remember that limestone is soluble, and rainwater combined with carbon dioxide forms auric acid, which is carbonic acid, and that can dissolve the limestone and eventually form caves. And it's that dissolution process and the landforms and features that are formed is known as the process of karstification. And then when water moves through this karstified limestone, that's the field of karst hydrology. And karst limestones have a unique feature, and that is that it has a triple porosity, 3 different types of ways that water can move from the surface to the subsurface. There's multiple types of recharge pathways. The first is through the pores in the limestone bedrock. That is if the limestone has pores and they haven't cemented up over time. That's the first type of porosity. The second is through solutionally widened fractures. So there might be fractures already present, and these have been widened as water moves through them. And then finally, as those fractions get widened further into conduits or caves, water can then move through those caves as well. So that is the triple porosity features that limestone and karstified limestone is known for. And that's what we need to try and model. If that all sounds like a complex set of processes, well, it is for understanding groundwater recharge through karstified limestones. This figure shows all the different potential flow paths in a karst system. It's taken from a paper by Andreas Hartmann and colleagues in 2014. You can see we have all these different runoff processes that could take place on the surface. So we have water moving through the soil into focused recharge zones, a closed depression like this one here and this one here. So this is water movement through fractures, the second of the types of porosity. You might have water also moving down through here, through the pores. That's the primary source of porosity. And when that water reaches caves or conduits, like this feature here, then you get the chance of having that third type of porosity, which is conduit flow. So here's the water table, and when the water reaches the water table, you see it's in this model, it's going down through the fractures and the caves into the conduits where it's been rapidly transported, and eventually it will leave the groundwater system, in this case, as a spring. The combination of all these different processes means that if you look at a spring discharge time series, which is this example on the right hand side, it's the water coming out of a karstified system, you can see it's quite noisy, variable, peaky. So it has high discharges, very rapid responses over time, compared to a spring that you'd find in a non-karstified rock type, where you'd have a much smoother discharge relationship with time, much less peaky and spiky. And that's because in a non-karstic spring, it won't have these rapid flow routes to get the water to move rapidly through the groundwater system and form these spikes. And karstification is a continuous process. So as you go through time, you get more calcite dissolution. The fractures and fissures will widen further. That will allow faster flow. That will allow more calcite dissolution, and so on. It's these processes that we have to capture somehow in a model if we want to then be able to model karst recharge. And this is one solution for how to produce a model. Again, this is from Andreas Hartmann and his group. And the example I've showed is something called the var karst R lumped parameter model. Lots of different terminology in that, so I'll explain all those different things. I'll start by talking about the lumped parameter model. A lumped parameter model is a model where you lump things together into boxes or large areas. And you do that because you don't understand exactly what's going on. You can't model something at a fine scale because you don't know where the caves are. You don't know where the conduits are. You don't know how the water moves through the fractures. And because you don't know that, you can't model it. So the solution is to have a lumped model. You just bundle all these things together. So that's what this is. So it's a karst recharge variability model. And the figure shows the different components of the model. So if we start with figure A, which is this one on the top center, you can see the inputs and outputs from the model. So the model is driven by these large boxes here, where the input is precipitation and the output is evaporation. They're the main driving functions for recharge. It has two boxes, so it has a shallow soil karst zone and a deeper karst zone, and water is routed through these boxes, and if it gets to the base of the bottom box, then it is recharge and is quantified. It also allows for lateral flow, so when the upper surface is saturated, it allows lateral flow and then further recharge down gradient or into other parts of the model. The grid resolution, which is in figure B here, very coarse resolution, so this is running at the scale of 1/4 of a degree latitude and longitude. And that's because, again, we don't know the detail of the features within a smaller area, so we can run this model at a large area. And all of these complexities that I showed you in the previous slide and shown here in part C are all homogenized into one of these boxes or lump parameter areas. And inside this box, then, this is how it's actually working. And this model does need some parameters. It needs some input data, so it needs precipitation and evaporation, and it needs some data here in terms of how much water can be stored in the soil zone and in the limestone, and how quickly it moves through that. So it does need some parameters which are unknown. But if we have observed recharge, in this case it's from karst springs, then you can calibrate the model because you have the input from precipitation, an output of evaporation, and an output from the springs, and you can calibrate the model to work out what these parameters are, and then you can run the model into the future to look at different scenarios. And that's one of the reasons why you might want to model karst hydrology, or why you might want to model recharge. You might want to be able to predict or build scenarios for recharge under different climates. For example, future climate change. If we can predict or have an understanding of how the globe is going to warm in future decades, then we can have that as an input into our model, because that will affect how much water is evaporated from the Earth's surface. And if we understand how tree water use might change and tree transpiration might change with climate change, with changes in rainfall frequency or intensity or droughts, we can put all these terms into our model and we can build scenarios. We can say, what if? What if temperatures get 2 degrees warmer? What if La Nina events become more frequent and we get greater amounts of rainfall? And we get some idea of how the karst system will respond to that. Or we might want to build scenarios for different land cover changes. So this could be deforestation or change in land management. Most recently, we have accidental deforestation or short-term deforestation after wildfires. And again, we can model that because the main change that will come from deforestation will be in the evapotranspiration term, the amount of tree water use that happens. So even if we don't know exactly what that will be, as long as we have some data that allows us to estimate evapotranspiration and these different land cover changes, we can put that into our model we can keep rainfall constant or other parameters constant, calibrated against, in this case, for the example here, will be a spring. In our case, it could be water moving into a cave, and then we can actually understand something about how land cover change might change. And the other reason to run a model is that it will tell you something about the processes that are occurring that you didn't know before. There'll be something in the model that you find which maybe doesn't work in some parts of the model, doesn't work at some time of the year, doesn't work at one site, or it over predicts or it under predicts, or it behaves well. But all these differences between the model and the reality tells you something important. It'll either tell you something about the model and how to improve it, but often it tells you something about how the environment is working and how to better understand it. There's all sorts of adages from modeling and the modeling world, and there's a couple I've just paraphrased down the bottom. Rubbish in equals rubbish out. If you put bad data into a model, you'll get bad model output. So you have to take care with the model inputs. And another quote, which is often misquoted or changed, is all models are wrong and some are useful. And that's true. All models will be wrong. No model can perfectly represent whatever you're trying to model. But by going through the modeling exercise, your understanding and your learning will be deeper, and you will quite likely find out some new knowledge that you didn't or wouldn't have known without going through the modeling exercise. So that's why it's important to model. I'm going to give a case study, and the case study then is from the Macleay karst of the mid-north coast of New South Wales. That's shown in this smaller inset box here. So the inset box is the same as this Google Earth image. And we have cave sites where we've used caves as observatories, and these are the yellow dots situated on the Google Earth image. Some are in the upper Macleay catchment, so this is in the rainforest headwaters of the Macleay catchment. That's the example from the top picture here. You can just see the cave exiting from one of the caves for scale. And we also have a series of caves at one location at a place called Yezeba in the lower Macleay. This is the block of karst situated in the lower Macleay, and it's absolutely full of caves, and we can use those to estimate groundwater recharge. This site is particularly useful because this is the floodplain, this is an isolated hill, and we can look at the caves here. The rainfall source area is only this hill, so we know that we get rainfall recharge for sure, and we know there's going to be recharging the groundwater here. And the note that this picture was taken in the middle of the 2019-2020 bushfire seasons. This is in late 2019 during a period of maximum drought. It's before the drought was relieved, and you can see the trees are really struggling on this hillside. They've had not enough rainfall, they can't access the recharge zone, and there's huge amounts of leaf loss, and the trees down in the lower part of this hillside, they're still green. They can tap into the floodplain and the deeper waters down here, so we can actually start to see the effects of tree water use just from this one picture. And this is the data set. This is the observational part of the study. So the first part is the observations, the second part is going to be the model. So the observations that we have here then, starting from the top of this very complex figure, so figure A, this is the daily rainfall amount, and we have this on weather stations dotted around the catchment. This is for the period from July 2014 through to July 2019. Data collection is still going today, and we have more data for anyone that's interested in working on this. You can see that rainfall is pretty consistent through the year. Maybe there's slightly less rainfall on the mid-north coast in midwinter, so around about July each year. There's often a dry phase, and you can also see some very high daily rainfall totals, and they often occur. So there's rainfall here over 150 millimeters here in 2016, here again in 2018, and there's been more subsequent to this time series, and they typically occur in spring, maybe late summer, and it's when you get the strongest amount of moisture development from the monsoon trough heading down the east coast of Australia. So you get these strong northeasterly trade winds, Sometimes you get an east coast low associated with it if it occurs later in the year, and you get these huge rain dumps. Figure B, second figure, is the daily actual evapotranspiration. So we need precipitation for the input into our model and evapotranspiration for our output. This comes from the Australian water landscape model. So it's modelled, not actual evapotranspiration, so it's the best estimate we can get. You can see a strong seasonal cycle there, where you have the highest evapotranspiration in summer, the lowest in winter, highest in summer, lowest in winter. That's because evaporation is highest in summer and lowest in winter, following the seasonal temperature cycle. You also get tree water use, which is the transpiration term, and that you can see, especially in some of these spikes. So when we get these very wet periods, then the trees can actually use more water and the transpiration goes up. But I think the important thing here is to look at the scale. So the daily precipitation scale goes up to from 0 to 200, the daily evapotranspiration goes up to 0 to 10. So you can have orders of magnitude more rainfall than evapotranspiration on any given day. And you can work out a water balance. That's figure C. So this is precipitation minus evapotranspiration, and that's run over time, so it's a cumulative water balance. And you can see over time, this value gets more and more positive. So we're getting increasingly more rainfall compared to evapotranspiration. And you can see these jumps up in the water balance, which occur with these high rainfall events here in 2017 and again in 2018. In the caves, we can measure recharge. So we have these recharge hydrographs in figure E down the bottom. You can see rapid increases in recharge, often within periods of no recharge. And we went through this data set and we counted the number of recharge events. There were 31 recharge events that occurred across the cave systems in the Macleay system over this 5-year period. So already we have an understanding of how many recharge events there are per year. We know when they occur, what time of year they're most likely to occur, and you can see there's a definite clustering of recharge events that occur around the summer period, summer into spring, which matches these wetter northeasterly trade wind rain dumps. And we can look at the antecedent rainfall for each one of these recharge events. For all 31 events, we can see how much rain occurred prior to those, and we can work out a rainfall recharge threshold. We can work out how much rainfall is needed to generate a recharge event. And we can't do that by any other method. And this is what we get. Just look at the top half of this table. I'm going to show this again in 2 slides' time, where we'll look at the bottom half. So the top half is the recharge thresholds, and the bottom half is the model output. So for the recharge thresholds, we considered the lower Macleay and the upper Macleay separately, because they have very different vegetations. The upper Macleay is much more subtropical rainforest. The lower Macleay has a slightly more temperate rainforest feel to it. And we looked at how much rainfall occurred in the 7-day before the recharge event, the 14 days before the recharge event, and the 21 days before the recharge event. And we did this because we don't know how long it takes the water to get from the surface to the subsurface. In reality, having done this analysis, we could work out that 7 days was perfectly reasonable, and the water routed from the surface to our observation site in less than 7 days. But we had to demonstrate this was the case. And we have some means, medians, and minimum values for how much rainfall is needed. If we take the median, which is a good measure of central tendency, then you can see 76 millimeters of rain over the course of 7 days was needed before you get recharged in the lower Macleay, and 79.4 millimeters of rain over 7 days to get recharged in the upper Macleay. So essentially they are the same values. We weren't sure if you have so much rainfall, like these 200 millimeter rain dumps, that the median was still a useful measure. Maybe the minimum amount of rainfall is also a useful indication, and so that's why we looked at the minimum. So the least amount of rain that was ever needed to generate recharge was 33.3 millimeters in the lower Macleay and 30.1 millimeters in the upper Macleay. So that's quite different from the median, and we didn't know why. And this is where the modelling comes in. If you run a hydrological model through this data, and we start to see when these different rainfall recharge thresholds occurred and whether it fits the model, then we can start to understand our system better. So let's go and have a look at the model. This is the model that we used. It's not a complex lumped parameter model, similar to the one that I've shown in previous slides. This is a simpler model, often called a bucket model or a reservoir model, because it has a single bucket or a single reservoir in this model. And we are looking at the inputs and outputs of a bucket. And this is a bucket which has a leaky bit at the bottom, so water can drain out the bottom. But when the bucket's full, it can overflow, and that's one of our knowns. So we're going to run this model. We know when the bucket is full because we see recharge in the cave. That's the recharge events that we observed over the 5 years in the previous slide. We know the rainfall going into this model, and we know the actual evapotranspiration of the water leaving the model. So the only unknowns are the size of the bucket or the reservoir. So we've called this the soil and epikarst storage volume, or V. Epikarst is just a technical term for the near surface part of the karst geology. We have an unknown term here, an unknown drainage term D, and this represents all the other sites that we're not monitoring. Because we're only looking at a few sites in every single cave, we're only capturing a fraction of the total recharge. So some of the recharge will be going in a different direction, and there's going to be other caves that we're not monitoring at all or don't know about. But that's okay. We can parameterize this model. We have good input and output data. We know precisely when recharge occurred. We have two terms that we need to parameterize, and we can do that by optimizing the model, which is this figure on the left-hand side. And we run the model using all sorts of different configurations of the volume V and the drainage term D, and we look for the models that have the least deviation from the best fit. For the Upper Macleay example here, this is the drainage term D, and this is the storage volume, or we've called it here the overflow capacity, how much water you get until you get overflow. And for the Upper Macleay, you'll see that the model parameter suggests that the storage volume is between 80 and 90 millimeters of rainfall equivalent. So if you imagine that you'd need to have 80 or 90 millimeters of rainfall instantaneously to fill that store, and not much of the water is drained out. Less than 1 millimeter per day is drained out to other missing locations, so we're capturing most of it. And that model captured correctly 19 out of 27 events that were simulated in the Upper Macleay. And the Lower Macleay model didn't perform so well. It did suggest a lower overflow capacity of about 60 or 70 millimeters. It definitely isn't the same as the Upper Macleay, and it suggests there's a much greater amount of water that's draining via other routes that we don't know about. And the optimum only correctly simulated half of the events. So by running this model, we've learned something about our karst system already. We know there's a difference between the Lower Macleay and the Upper Macleay. We know that there's more storage in the Upper Macleay soil and epikarst compared to the Lower Macleay, and we know that our model is not working so well in the Lower Macleay compared to the Upper Macleay for reasons that we'd need to investigate. And this model is available on the GitHub site, so if you want to go and explore it yourself, you can go to the Karst Lab, the Karst Hub on GitHub, and there's a simple water budget model coded in R, so you need to be familiar with R, and you can run the same model that's used in this data set, which has been published. Now we can look back at the summary table and the bottom half where we look at the water balance model output. And this summarizes the Lower Macleay and Upper Macleay for the overflow capacity, showing it was lower in the Lower Macleay, the drainage term, which was higher in the Lower Macleay, the number of observed events and how many were correctly simulated. So here we have 7 out of 14 in the Lower Macleay, 19 out of 27 in the Upper Macleay. We also looked at the number of observed events that were not simulated. So there were 7 that were missed in the Lower Macleay, 9 that were missed in the Upper Macleay, but also the number of simulated events that were not observed. And in the Upper Macleay, the model simulated extra events that we didn't see. So that tells us something about how the model was not functioning correctly. To summarize both the observations and the model, our observations demonstrated that we needed between 76 and 79 millimeters of rain in a week to get recharge. And without using caves as an observatory in this region, we didn't know that before. This figure actually compares well to Australian estimates for water table fluctuation from isotope methods and chloride mass balance methods. Often these are annual, but if you then convert them down to weekly or monthly, that comes down to about 100 to 200 millimeters per month for Australia in general. So our results suggest that actually most of that rainfall probably occurs in a much shorter time period, probably less than a week. And our modelled soil and epikarst water storage capacities of 67 to 77 millimeters of rainfall equivalent corresponds very well to this value here, which suggests that you get recharge after 76 to 79 millimeters of precipitation over a week. Of a similar order of magnitude. So that gives us confidence that the model is making sense and it's doing a good job. It's realistic. But we also had these model misfits. So there's very poor agreement with the model in the Lower Macleay site, and we also had extra events generated by the model which weren't observed. And by looking at further detail at when those occurred and at which site, we realized that what we needed to put in our model was an extra water loss term from the deep rooting from the gum trees at both sites. So we had to add into our model a deep rooting zone. And when we did this and we increased the evapotranspiration term by allowing more water to be lost from this part of the model here, then we actually managed to get a much better model fit. So we learned something about our system. We learned that the actual evapotranspiration that we used was not correct. It was underestimating the real evapotranspiration, and that's because it didn't account for extra tree water use from deep rooting. That highlights one of the advantages of using models. You always find something new. With that, that's the end of the set of slides, and it leads you now into the assignment where you'll be given an observational data set, and you'll be given this model, the simpler version without the deep rooting zone, and also not coded in R but in Excel, so anyone can use it anywhere. And you'll be asked to go and investigate a different groundwater recharge set of information, and that'll be from Cathedral Cave at Wellington.